Welcome to my new calculus channel. I am John Gabriel, and in this exciting episode or YouTube video I'm going to be discussing how we got numbers. That's right. This is a topic that even mathematics professors don't really know very much about, and I'm talking about professors who have done maybe 4 to 7 years of studies in mathematics. I'm going to make a very arrogant statement, although I don't really feel arrogant because it's actually true. After Euclid and before me, no one had a clue what is a magnitude and what is a number. And no one really understood how we got numbers. For example, if you look at the thousands of books that have been printed on how we got numbers, they're full of misconceptions, illogicalities, and nonsense. For example, a lot of educators think that natural numbers came before fractions and before ratios. That's actually untrue. Natural numbers came way after ratios. So also, what do you think? Do you think we got ratios before measure or measure before ratios? I'll let you ponder that question for a while and you'll be able to determine the answer to that later on in this YouTube video. In the meantime, I'd like to start off with a definition of magnitude. Magnitude. Well, the Greek word for magnitude is megathos, and the plural is megethous. Okay. Magnitude is an idea. It's not a number. It's an idea. It's an idea of dimension, size, extent. In other words, how big, how small, how fat, how thin, how tall, how heavy, how light. You get the idea? I'm sure you do. Okay, so now, that is what a magnitude is. It's just an idea of size. It is decidedly not a number. Okay. So, the ancient Greeks, who were unbelievably smart, in fact, they were so smart that no one today could even reach their level of intelligence. The greatest mathematician in history was Archimedes, by far the greatest. People don't realize what Archimedes accomplished because they know very little or no mathematics, and that goes for mathematics professors too. So Archimedes actually produced some really incredible works, and they were also based on incredible works that were produced before him. For example, Euclid had written several books, including the Elements. Euclid also wrote the Conics, which was lost. There is no record of the Conics anymore. I don't know whether this was possibly a part of the manuscripts in the library at Alexandria or not, but anyway, that will always be a mystery. Archimedes wrote the works of Archimedes, which were thousands of years ahead of his time, and up till this day usually are not touched till way after a master's course in mathematics or a doctorate, preferably a doctorate, I'd say. Now, coming back to a magnitude, here are two magnitudes. They don't have to be distances or lines. They can be masses, they can be volumes, anything else. How can we measure these? How can we measure these? Okay, the Greek word for measure is meson or mesonas. Okay, how can we measure these? Well, if we don't have numbers, which we don't at this stage, let's pretend we don't, what can we tell about these two lines? Well, we can tell that this line here is shorter than this line, yes, so by doing so, we've actually performed some kind of measurement. Well, if this line is called AB and this line is called CD, we define a ratio AB excuse me, to CD, AB to CD, and this is read literally as AB compared with CD. AB compared with CD. Okay, so what we're saying here is, if we compare AB and CD, what is the outcome? The outcome is that AB is less than CD, or CD is greater than AB. And we have performed something called qualitative measurement. Okay? Qualitative measurement is measurement without numbers. Measurement without numbers. However, if we had, let's say, a line like that, and we had another line, let's just grab the same line, copy, paste, and another line like that, and now we compared those two lines. Now you know, obviously, because you know they're equal because you saw me copy and paste, but let's suppose you didn't see me copy and paste. If you can't tell that these two lines are different, then you can't perform any measurement, can you? Of course not. So the only time you can perform qualitative measurement or qualitative trichotomy is if you can tell for sure that these two lines are not equal, as we did here in the case of AB and CD. Alright, so just to recap here, a ratio is literally the comparison of one magnitude with another magnitude. And I can tell you right now, it's no coincidence that Euclid defined ratios in Book 5 well before Book 7, where he defined numbers. Okay? In fact, Book 5 defines magnitudes and ratios. Okay? The Euclidean definition of magnitude is circular, therefore it's not very good. A better definition for magnitude is just that it is the idea or concept of size, dimension, or extent. So that is what is a magnitude, and that is the first step towards measurement, or the first measurement, qualitative measurement. So now, let's get rid of this and cut it. Right. Let's carry on. So now that we've established what is a ratio, just having two lines or two magnitudes like that, yes, any two magnitudes, doesn't matter. Any two magnitudes. Copy that and paste it. Oops, there we go. So if we just have any two lines like that, we need to be able to tell how to measure them. And if we can tell that they're not equal, so let's put another one more line. Let's say we have these two lines. If we can tell that these two lines are not equal, that's all we can say. We can say that the one is less than or the other one is bigger than the other one. But we cannot say how much bigger is this line than that line. Let's make it red. So we cannot tell how much bigger is the red line than the blue line, or how much smaller is the blue line than the red line. Now notice I'm using distance, but magnitude can be anything again. It can be mass, it can be volume, etc. And I'm only going to deal with length, in other words distance, in this particular topic, to show you how we got numbers, to show you how the Euclidean derivation of numbers happens. Perfectly, by the way. And I'll tell you something else. Well-formed ideas are independent of the human mind or any other mind. Whether we existed or not wouldn't affect the existence of the concept of numbers. They have existed eternally and shall continue to exist eternally, whether there was any consciousness or any mind, or whether there was a creator or God or anything like that. That's completely irrelevant. numbers, the perfect derivation of numbers, in other words, the perfect concept of numbers, has always existed, whether we thought about it or not. Okay, that's a little philosophical diversion there, but it's important. Just give me a moment. So, how can we get some better measurement for these two lines here? So far, all we've seen is that we can tell that they're not the same length. One is smaller and bigger. But how can we tell by how much? Well, we can't do that until we introduce a very important concept, the concept of the unit. In other words, we pick any line we like, this line or any other line, and we say that it is the standard unit. Okay? And so, if we choose any particular line as the unit, then we can, and given any two lines, if both of those lines are expressed in terms of units, then we can tell how different one line is from the other in terms of the unit. Okay, so the unit is just basically the ratio of one magnitude to itself. So let's say we have the magnitude u for unit to u, and that is the unit. Okay, so the comparison of the unit to itself is the unit. Okay, so now that we have the unit, we can say, well, if this line is 1 unit and this line is 2 units, now we can tell the difference between these two lines, can't we? Of course we can. The difference is 1 unit, right? And if I extended this line like that by another unit, the difference now is 2 units. This line would be 2 units less than this line, and this line would be 2 units greater than this line. So we could call this line here whatever we wanted. We could call it alpha, we could call 2 units beta, we could call 3 units gamma, right? And so we know that alpha plus u is equal to beta, right? Plus means if we place these units adjacently, these lines adjacently, this line adjacent to the unit. So if we take alpha and we place it adjacent to the unit u, we're going to get beta, right? So here we've got beta, and so on. And so we can give these lengths names, and what we have in essence done is derived those numbers known as the natural numbers. Okay, the natural numbers. The natural numbers are ratios of magnitudes, let's say m, to the unit, where m is composed of units. Okay, so natural numbers are magnitudes where m is a magnitude composed of units to u. And really it wasn't written like that first, it was written like this. So the natural numbers are really ratios of magnitudes to units. I'll explain the difference between the vinculum here and the colon a little later, but I have also talked about it in another video. So okay, so now that we've got natural numbers, we think to ourselves, well, if we have any two magnitudes, any two numbers now these are numbers. If we have numbers 1 and 2 like that, so this is 1 and 2, we can tell the difference here, okay? We can say that 2 is equal to 1 plus 1, right? 2 units. And so once we have numbers, we can form ratios of numbers, right? So we can form a ratio of 1 to 2 or 2 to 1. Now 1 to 2 tells us which of these here is the unit. Can you guess? 1 to 2 tells us which of these two lines is a unit. If you guessed 1, you'd be wrong. 2 is the unit in this case. 2 is unit, yes? Okay, and obviously in this case here 1 is the unit. This line here is the unit because we've got 2 of those units. We always write the unit in the consequent part of the ratio. Consequent part. And we always write the antecedent before the colon. Antecedent. Okay? So now we have formed something called fractions. So now we have fractions, and if we want to go a step further and say this isn't just a comparison, it's a number, then we'll write 1:2 as a half. And now it's no longer just a comparison, it's a number. And what it means is the unit divided into two parts, and we're considering only one of those parts. Similarly, if we have 2, 1, we have a unit like that, and we have two of those, right? So it's 1, 2. And we write it as 2/1, yes? So it means we have 2 units, yes? 2 units. Okay, so now we basically derived the fractions or the rational numbers. Rational numbers are ratios of natural numbers, rational numbers. Guess what? There are no other numbers besides these numbers. Oh, yes, I know about and have studied and have been through school and university. I know what irrational numbers are. And I'm telling you, they are not numbers. Okay. And why are irrational numbers not numbers? Well, because they cannot be measured in terms of a unit, or if you have two of them, they cannot be measured in terms of either one. And the correct name for those type of magnitudes is incommensurable magnitudes. They are irrational, but they are not irrational numbers, okay? So incommensurable magnitudes are irrational, which means they can't be expressed as A over B, but they are not irrational numbers. Okay, because they can't be measured. Let me just write down something really important here. A number is the measure of a magnitude. A number is the measure of a magnitude. You will have noticed up till now that this video is very elementary, but a lot of professors of mathematics would be learning a lot by just watching this video because they don't know these facts. So, a number is a measure of a magnitude. Very good. Incidentally, all the videos that I create are all impromptu. I don't really sit down and plan them. I simply don't have the time. So if there are any errors, they're unintentional. Just letting you know that. So what are irrational or incommensurable magnitudes? They're magnitudes that cannot be measured. You might say, okay, well, what about the square root of 2, where you have 1, 1, and you write 2 like that? Now we know that the area here is equal to this area plus this area. You might say, well, since this area is equal to these two areas, the square root of 2 squared is a number, right? So why is square root 2 not a number? Because square root 2 cannot be measured in terms of the unit. In other words, you can take, here's square root 2 again. 1, 1, square root 2. You cannot take this unit, let's say it will go up till about there, and that'll be a unit, right? So that's about a unit. And what's left there is incommensurable still. But you can get 4/10 out of that. So let's blow this up so you've got a unit, and over there you can get 4/10. But there's still a part, not the whole thing is 4/10. There's still a little part here which can never be measured. It's called the incommensurable part. And so if you blow that up further, you'll have 1 unit, 4/10, and over here you'll have 1/100th, and this part here remains unmeasured. You can keep on measuring, trying to extract or measure a rational number from that forever. So eventually you end up getting 1.41 ... That's the square root of 2, right? Approximately, by the way. It's not equal to, it's approximately equal to that. And I don't want to spend too much time on this. I've written a very nice article on how we got numbers. It's at my LinkedIn site, and I would recommend that you visit it and read it. It's called How We Got Numbers, and it has some very amazing facts which you've never heard of or seen, because I'm the first to publish these. And it explains exactly how you can derive the concept of number, what I've just told you. Yes, and a lot more than that. It gives you the new axioms. You've probably all heard a lot of, if you've been to university and you've studied advanced mathematics, you've done Zermelo, Fraenkel axioms, and also the Peano axioms. All of this set theory is a load of junk. This is junk, okay? It's junk in more ways than one. It is so flawed that it's not even worth studying. I'm just going to beat a little on Peano. He was an Italian mathematician who created 5 axioms, but he really made a spaghetti mess out of it, because his very first axiom says 0 is a number. So poor Giuseppe, that's his first name, didn't realize that you can't just assume that a number exists, and you can't just make an assertion like this and pretend it's true. So the rest of the axioms are also equally stupid and equally illogical, but I'm not going to spend time on these axioms. I've written a lot about it on Sci.Math and also in other forums. You can read on Sci.Math, a lot of those will be called the Peano crap axioms. So if you do a Google search, crap axioms, you'll find lots of information on that. I don't even care to waste my time in it, or yours, but you may waste your time on it if you want. That's no problem with me. Okay, so that's pretty much it for this video on how we got numbers. I will put some links in the comment section of the YouTube video. I have a lot of videos that I've created, and I'm constantly uploading more videos at my site. So please visit my site and check out my videos. And so this is the New Calculus channel. I'm John Gabriel, and I hope you have enjoyed this YouTube video. Take care. Till next time.